Oh, right. Yeah, I can get it. I have worked on my No, but I can put it on my laptop.
Thanks for being here. We have the, well, actually usually we have Jaap's Outlook lecture that he gave yesterday as the final lecture in the course, but because we have needed a session for the reading, the writing lecture last week, we shifted the research highlights to today. So we have 3 items on the menu for today. Because nobody wanted to start early, I take the first slot and I do prediction of protein interaction positions for the sequence, which is already on the projector. And then Olga takes the next one where she explains work out of her master project that's leading up to 2 papers, more or less, where we look at epistasis, gene-gene interactions, and how to model the possible mechanisms behind it, and all of it. And then at the end, last half hour, Maurits will do a lot of aware multiple sequence alignments. You might have heard from Jaap about his multiple alignment tool, Praline. Massively worked on that for the last couple of years. You haven't really seen him, I think. Usually, also, previous years, he was also assisting in this course. But he's a PhD student in our group. He also did this master. And he's been working on further development of Praline, and he will tell you about how to make multiple alignments with awareness of previously known functional motifs, which is a very useful feature. Okay, so I'll draw before the next ceremony. And I don't know if not everybody is here, or it looks like there's fewer people because this room is so big. Anyway, so I'm almost there. Last item. So the story, my story. So I should take 20 minutes. So each presentation should be 20 minutes, and then about 10 minutes for questions. So I hope you've brought good questions. You've read the papers. Oh, all this paper is not on. I don't think it's on Commons, is it? No, it's also not exam material because it's not strictly not published yet. Last week, when we decided, or 2 weeks ago, when we decided to announce it to this paper, it also was published. It was accepted last Friday, so we're safe there. So these are published papers, and this one is on its way, but it's not quite there. Also because we think 2 papers is more than enough for you guys to prepare for the exam. We didn't want to do a third one, obviously. It's nevertheless an interesting read, and I'll ask Olga if we can put the manuscript on canvas for you to read. Right, okay. So, yes, my time is ticking. So, the title of this is the title also of the paper, Seeing Trees Through the Forest, Sequence-Based Homo and Heteromeric Protein-Protein Interaction Science Using Random Forest. It's almost an abstract. I like long titles because they tell you a little bit. It's like long variable names when you're programming. They tell you a little bit what's going to be about. So what we've done is we took, we start from the sequence, and then we try to predict not whether a protein will interact, but if it interacts, what are the residues that it will most likely interact with. That's a very useful thing. You could, for example, map that back to known SNPs and see whether one of your SNPs lands on a predicted interface position, and then it's maybe more likely to be disease-causing. This is something we try to test. Actually, Rihanna, are you here? Oh, no. Rihanna, no, both did a bachelor project with me, and Tim did something else, but Rihanna tried to test that hypothesis, and it looks like it might be true, but then you need better data to make a firm conclusion. That's another story, but this can be very useful, that's the idea. And of course you can do structure-based predictions, but then you need a structure and you don't always have that. So that's why sequence-based predictions are nice. Now, we started off with doing this for homomeric proteins, and then that turned out to work quite well, but all the other methods were sort of leading towards heteromeric interactions. So where there's two different proteins interacting. Homomeric interactions are when the protein interacts with itself to form a homodimer. Not with the same molecule, with another molecule of the same protein type, right? And so we extended it to predict heteromeric proteins, and then because everybody who was developing methods like this was saying in their papers, like, it's so difficult to do both, and we found it to be relatively easy, which I'll show you in a minute. That's why we came to seeing the trees through the forest, because it looks like a nasty problem, and it turned out to be slightly easier than this way. Sometimes you're lucky. Okay, so one step back, protein function. I already mentioned SNPs. This is, anybody recognize what this is?
Synapse.
It's a synapse. Why do you know it's a synapse?
Well, the shape one, but you see the vesicles. Well,
Yeah.
it's really addictive.
Very well spotted indeed. It's a vesicle. But this is not a real image. This is an artist impression, but it's not just an artist impression. It's a well-informed artist impression. And what they did here is they measured for as many proteins, known vesicle proteins, as they could. They measured the location and the quantity of those proteins inside. So this is sorry. I can only say one thing at a time. Sometimes there's three things that want to go all at the same time. Yes, inside this vesicle, they measured all these proteins that they know that should be there, and they measured their approximate location and their approximate quantity, and then they gave this to the artist. I don't know if they did this themselves or there was another guy or a girl, but they made this impression, and then for many of these proteins, also the three-dimensional structure is known, so you can actually draw in all the proteins in approximately the right place and the right amount. And you know these vesicles, and you know that there's membrane proteins associated with these vesicles, and there's proteins that are supposed to be inside these vesicles, and so on. There's filaments and all sorts of other cool stuff there. But before I continue, this was the other thing that was popping up in my mind. Who doesn't know what a vesicle is? Okay, so you can also say this is synaptic bud. So this is the leading end of a neuron. This is the part that, so this part extends all the way to the cell body of the neuron, which can be a meter away or so. If it goes from your spinal cord to your toes, it's a meter and a half, depending on your size. For giraffes, it can be much longer. But this, so this, what's the word for it again? And it doesn't matter. This thing that leads up to that's not in here. This is the bud, and this one connects out to the receiving cell. And these vesicles actually contain the signal molecules that are at some point excreted and are detected by the receiving cell. Yeah? Thank you for filling in the name, but that's not so important. Okay, so if you want to know more about this, ask him. Of course, he probably knows more about it than I. Okay, now back to the protein, to these proteins. So all these proteins are in the right amount, in the right location. But if you would build a car this way, then you would have all the engine parts in the engine compartment. You would have a wheel at each corner of the car. You would have all the seat components in the passenger compartment and so on. But they wouldn't be connected in the right way because the interactions aren't in the air. Okay, so the proteins are in the right place, but they're not assembled in a way. Yeah? So if you would try to build a car like that, you open the engine compartment bits are there, but they're all slightly off. They're not connected. The pistons aren't connected, and the cog wheels aren't connected. So the missing thing here is protein interactions. So this is always my introduction to why I think protein interactions are important. So it's understanding these interactions, but also being able to predict these interactions so you can understand the protein function and cellular function at a larger scale. It can be useful, as I already mentioned, in distinguishing between impactful and less impactful SNPs. And for example, if there's new viruses being discovered, often you don't have structure information for many of the proteins in new viruses. Like a new virus genome typically has half its proteins completely dissimilar to any protein that we know. So you couldn't even make a homology model if you wanted to. So it's very useful to be able to do this without having structure knowledge. Okay. Now, that's one part of the protein interaction. The other part of the protein interaction is what is it actually? Because there are different levels at which you can define protein interactions. And the most sort of distant way is influence, like gene-gene interactions, where you measure basically correlations. When you do a knockout of one gene, you see an effect on the other one. Epistasis is actually an example of that. I'll leave that to all that. So that's also interaction, but that's not what I'm talking about. This can be direct, where A influences B. It can be indirect, where A influences C, which then influences B. And I think Olga will have an example of that as well. It could be mutual dependence, where C regulates A and B. Therefore, you also see a correlation between A and B. And this is all interaction, but it's not the type that I'm talking about. Because the one I want to talk about is direct physical interaction, where two protein molecules are actually physically in contact and they stick together. Yeah? Like a nut and a bolt, or a wheel being mounted on an axle or a car. Okay, so it's contact. It might look something like this, but it's of course not with proteins. And there's two sort of general ways. It can be two different proteins interacting, or it can be two of the same protein interacting, two molecules of the same protein. And that would look a bit like this. So you see it's the same molecule, but then it's rotated 180 degrees. So it's the same interaction side, which then it's like a Siamese twin, but then different. Okay. Okay. So and then finally, so what we're interested in here is not if these proteins will interact, but which residues in the protein are most likely to be on the interacting interface, the interacting surface, which we call interface. So, now, then to sketch a little bit the landscape, because I'm not the first one to try to do anything about predicting protein interactions, there's a couple of types of methods that you can use for this, and there's a couple of very nice reviews from the group of Alfonso Valencia in Barcelona. I was completely confused because, of course, Valencia is also a town, a city in Spain, but he is in Barcelona. He's still there. Okay, so he's retired. He's a retired scientist to just go on doing science, usually. Okay, so he has done a lot of work, and he's not the only one, but he's done a lot of work in that, from sequence-based methods. And one example is called mirror tree, where you use the evolutionary history of two protein families, and you make a phylogenetic tree of one protein family and a phylogenetic tree of the other protein family, and then preferably you should have the same species in both sets, and then you can compare the two trees, and if they have the same shape, then you can infer that these two proteins, during their evolutionary history, have had the same kind of selective pressure, because otherwise the trees would look different. If they have the same selective pressure, then they are most likely involved in the same function, or they're related, and they might be interacting. But it's a very indirect evidence of interaction. So some proteins actually, so interacting proteins will show the same phylogenetic tree, typically, not always. But there's other reasons, more indirect reasons, why two protein families can also have, like two enzymes from the glycolysis pathway, for example. Any two enzymes from the glycolysis pathway will probably have a very similar phylogenetic tree. But they're not necessarily interacting. Even if they're in the same pathway, they're just acting on a string of ligands. One ligand comes from one enzyme to the other. The enzymes could interact, but they don't have to. Yeah? Okay. So it's fast, it's easy. You can nearly always do it because we have a lot of sequence information, and this review was written in 2001. We have a lot more sequence information now, and it already works very well. It doesn't give you any quantitative information about interactions, it just gives you some idea of, oh, there might be something related. Now, on the other end, sort of the spectrum, there is protein-protein looking, where you have the structure, and you can do all sorts of biophysical calculations to match these two structures together and see how well they fit, and measure the interaction strength from simulation and so on. And to do that quantitatively, you need even more. How to say that, more detailed calculations, but that's not the lecture that I'm going to do today. I have a different one. This will be in the structural aspects. So this is sort of, you can sketch sort of a landscape here where this is more knowledge-based, and for this side is more first principle. There's something off with my font. This says first principles, but it's in white, on a white background now. It was supposed to be here. This should say knowledge-based, and knowledge-based. Knowledge-based first principles. This is for first principles, as first principles as we can do in biology. It's not first principles as they do in physics, where you start from like a couple of basic assumptions, and then you derive the value of E and the charge of the electron and so on. That's first principles. This is also first principles, but different. But here you use all the knowledge, all the data, or a lot of it that we have from protein on proteins. Okay. So this is what the lecture is going to be about. If you're interested in this part, there's a reference here, but it will also reoccur in the structural diagrams. Okay. I'll skim over this one just to say that what we're doing is, at this level, we're doing residue-based prediction protein interaction interfaces. There's other methods that also do that in a slightly different way. If you want to know more about that, this is another review from the group of Valencia, more recently, 2013. This is not important. Okay. So that's the background of protein interactions. Now what we're doing is a random forest predictor. So it's machine learning. So it's basically a classifier interface and non-interface. You try to predict that. You train a classifier to do that. So what do you need to make a good classifier? Any ideas?
Yes.
A test set. Okay. Yes. Sorry. A training set. Yes. Well, I probably in the other order. I should refer to the training set. But if you only have a training set, you don't have a test set, then you're also in a bad shape. Oh, I am mirroring. I want to see what my next slide might be. What are my next words? Okay. So is that the ordering that we're... Oh, right. Yeah. No, I started from the other end. So I started from the feature end. Right? Because you also need features that are the input for your method. So those basically the quantities that you know beforehand on which you can base your predictions. Okay, so and one easy trick to do when you're predicting interactions is, because there's already predictors that predict solvent accessibility, whether a residue in a protein is likely to be on the surface or buried. If it's buried inside the protein, it's not likely to be participating in the protein interaction because it's on the inside. Yeah? If I run into a wall, I'm much more likely to hit my head than my liver. I'm sometimes amazed by the strange analogies that I can. So separating buried from non-buried, that's relatively easy. So you use a separate predictor to do that. And then other features. So we'll come to test sets in a minute. But what kind of features could you use as input to predict? Well, this is one. If you can predict this from sequence, then this could be an input feature. What are other features that you think might be relevant for predicting protein interaction? can I just broaden that immediately to amino acid properties? Yeah, I can charge size, shape, polar, yeah, things like that, hydrophobicity. Okay. Yes. Oh, now I get it more. With size. You can also look at evolution, right? So because conserved sites are more likely to have a functional role, and then so if you're looking at a conserved site, it's a priori slightly more likely to be involved in an interaction problem. So accessibility, there's the exposed one. What we also use is secondary structure. Not that there's not a very easy one-to-one relation between secondary structure and protein, but loops tend to be involved in interactions a lot, and also better structures. Helices is slightly less, so it's useful to know. And another one that we can actually predict from sequence is flexibility. So there's a method that was published already a couple of years ago that does that. It's called Dynamine, and I'm still not sure why it works, but they've trained this on NMR data, which captures flexibility of the backbone angles to your protein in a quite clever way, and then on this you can actually train a predictor, and that works quite well. So these are the features that we use. So I like your suggestion. We tried that a bit. So to add amino acid properties, we tried that a bit, not a lot, but just a bit. And it didn't seem to help, and we don't know why. Apparently, these collection of features already cover whatever you could learn from the specific amino acids. So if the effect of a particular amino acid only works through these sort of secondary things, then you've already captured it in a different way. But we haven't tried it exhaustively, so I can't say whether it wouldn't add. We tried some of it and it didn't seem to help, so throw it out. Okay. And the final one is the length of the protein. And we actually had a run-in with this with the reviewers. So if you want to publish a paper, you send it to a journal, they send it to reviewers, which are just peers, other scientists, that then say whether they like the paper or what they like or don't like. And one of the reviewers said, you have to take out protein length, because it's the same for all positions in your protein. It's just one number. So how can it help you pinpoint this is an interface residue and this is not an interface residue? And our reply is very simple, because we tried without, and we said, well, we don't know, but if we try without, predictions become much worse. So why would that be? Why does it help the predictor to know the length of the protein chain?
Could be a starting bias.
Could
be a starting bias for the machine model.
Starting bias, in what sense?
Like a bias to...
Well, why do you need a bias on protein length? We checked whether for some reason or other, big proteins were easier to predict or something like that. So the predictor could skew towards some big protein families and be very good at that, and then average that out with being bad at small proteins. But that wasn't the case. But protein length is a proxy for the size of the protein molecule. And so what happens to your surface if you grow the size of your protein? So its solid accessible surface increases. But what increases more?
The inside increases more than the actual surface.
Yeah, so to increase your surface the factor of 2, you have to square the volume, right? So your volume to surface ratio, in whatever value you want, with the number of residues, for example, will change when you increase the size of your protein. So it means if you have a long protein, you should predict relatively few interface sites compared to when you're predicting for a small protein. Because the size of an interface is not going to change a lot. There's also no. The size range is about a factor of 2 or 3. And protein sizes can vary a lot. And so, because at some point, if you're thinking about a bigger sphere, at some point, you can't can't really make a bigger interface. Also, if you make a too big interface, it's probably going to stick to anything in the cell. And you remember the picture that I showed in slide 2, there's a lot of different proteins in the cell. So if you have a protein with a big sticky interface, it's going to be like a magnet in a scrapyard. It's going to attract everything. That's very likely going to be lethal to your cell. Okay, so that's why protein is. Okay, now, then you need test sets and training sets. So we have 2 sets. One was our home-built homodimer set that we used in the previous paper. It's quite large, high confidence, but because we wanted to go to heteromeric interactions as well, we actually took a training and test set of one of the other papers of another method, 2010. Also high confidence, but a very small set. Okay, now, I need to keep it where I am because I think I'm already talking for 20 minutes. Right. So, to get evolutionary information, you all know that, we've done it. You run blasts, you get an alignment, so you get homologues, or putative homologues, size, similar problems. But if your value threshold is, well, we call this lenient, because if you want to have real homologues, you need 10 to the minus 6 or so. This is smaller than what you've been using. It's still considered lenient. And then you make a proper alignment, because the alignments of blast mix aren't very good. And we use muscle, not because it's very good, we know protein is better, because we made it, but the muscle is much faster. And then, you remember these features that I told you about, we don't calculate it just for the input sequence, but we also calculate it for each of the homologues. So you get an idea then, not just of whether this is solid accessible alpha helix in a flexible width of the sequence, but you can also see whether these features are conserved throughout the homologues, or whether it's very variable. That will probably tell you. We're not sure what it exactly tells the predictor, but this helps with it. And we don't put all of these numbers into the predictor, but we just take the average there, which is sort of the evolutionary typical value of that feature. So it could be all alpha helix here, for example, and the standard deviation of it. So if we don't put alpha helix in, the predictor gives a propensity for like 80% likely to be alpha helix, so we put this propensity when you have a number and you take the average. So, okay. Now, when we do this, we also wanted to have an idea of which features actually have an added value for the prediction. So we start with doing them one by one, and you know the area in the curve of the rock plot. What is random? 0.5. So this is random. Yes? Significantly, statistically not different from random. So if you take a single feature, it doesn't work. Everybody knows that. That's not me. But if you start combining features, two of these features plus the protein length, it actually gets better. If you add a window, so you take the features of for the residue before and the 4 residue after the residue that you want to predict, so you take the local sequence neighborhood information into the prediction, it also gets a little bit better. This is just one feature. The other feature, but then you can do both of them together, plus the protein length, plus the window, and then this is sort of the first magical threshold. 0.6, below 0.6 is bad. 0.5 is random, below 0.6 is bad. So this is not bad anymore. It's not good, but it's not bad. So that's progress, right? If you just take solid accessibility, that's already better than random. That's not surprising because you just throw away all the buried residues, and then you expect to be better than random. Then if you combine that with the others that we already had, you got 0.64, but now we left out the windowing again. If you put that in, oh sorry, this was not the window. This was solid accessibility and secondary structure. You're getting near to 0.7. Above 0.7, you can say the method is sort of good. Yeah? 0.8 is very good, 0.7 is very good. You're getting closer. Now, what next? Well, we should put the window back in, and then we get this one. Plus the window. This was the last one on the previous slide with the window is 0.71. And then the final thing that we did was to realize that we have way, sorry? What I just said. So you have, sorry, I'll just draw it. So if you have your sequence, you're predicting for a particular residue. So you know what, I'm going to predict whether this residue is interface or not. So now we have all these features like alpha helix, gravity sheet, random coil, some accessibility, the second circuit already have, dynamics, right? Plus all these features for the average and the standard deviation of the homologs, right? So you have a whole column of features for this residue, but you have those features for each residue. So now if you take a window, that means that to predict this one, you also take the values of 4 residues upstream and downstream of the residue of interest. Yeah? So you have 9 times more information, data, for your predictor to work with. But you also, I mean, you know that the residue by itself is not going to be an interface. It's going to work together with other residues. Not just in the sequence, but also importantly in the structure. But we don't have that information. But this information we can know. You know, we know, it's easy. If they're close to the sequence, they're close to the structure. Okay. Now the final trick here is then to realize that we have about 20% of our protein on average is interface, the rest is not. So that means you know how you can optimize sensitivity or specificity that way, right? If you predict everything to be non-interface, you have an 80% accuracy. Because you only get all the interface pictures wrong, which is 20%. Yeah, so to help the method avoid that bias, you just chuck out 3 out of 4 non-interface positions, so you get the same amount of non-interface as interface. That's called balancing, and that helps a little bit. Not a lot, but it's important. Okay. You can also look at other performance features, but I'm not going to do that for such time. Now, this is the same things in rock plot, and now we compare it to other methods, and we can see that we're significantly better. So red is us, this is rock plot, this is precision recall, and these are spider and cyber, 2 other methods. Cyber is not very, very good. But the problem here is that those were trained on heteromeric interactions, and now we're testing them on homomeric interactions. It's sort of unfair. It's like having a method that's trained to play chess, and then you test it on playing checkers. Right? So we can do it the other way around then, to take our method and test it on their heteromeric test set, or not the cyber heteromeric test set, and then you can see that cyber is actually slightly better on this test set than on our test set. But we're even better. We didn't even train on their training set. Yeah? But that was fun. So then we were like, okay, but if we are already better when we didn't even train on their data, what happens if we train on their data? So this was the previous one. Now we train on the heteromeric data, on their heteromeric data. And that's the red one, that gets even better. Yeah? So now we have 2 predictors, and now when you come to me with a sequence and you ask me, can you predict my interface position, I'm going to ask you, oh, is it a heteromeric or a homomeric interaction? And you're like, oh, I don't care. Okay, so then we train a predictor that doesn't care. So we combine the 2 test sets. And I don't have the rock plot for that, but these are the previous ones, and this is the combined one, where you train on both sets. And you test here on the homomeric interactions, and you get the same performance. That's cool, right? So this was the previous 1.72. And then we do the other way around. We have the combined one, and we test it on the heteromeric data set, and then we get 0.64. With the heteromeric trained one tested on heteromeric interactions, we get 0.65. It's a little bit worse, not a lot. Yeah? So if you don't know, you should use this one, because it's good in both cases. If you know you're interested in heteromeric interactions, you use the heteromeric trained one, because it's slightly better. Okay, well that's the story. Oh, now, to cap it off, you can also look at which sites are predicted, and that's interesting, because there's apparently some sort of complementary complementarity between the two methods. So this is side with the old method. This is our heteromeric trained interaction thing. And these are the true sites according to crystal structures. So you can see that there's a lot of positions that we can predict. Sorry, over here. That we can predict, but cyber can't, and the other way around. There's also a lot of things that we both predict, that are apparently wrong. And some of those might actually be interface positions, but we don't know that because the two proteins might interact, but then one of those proteins might actually be able to interact with a third protein on a different position, different interface, but we don't have a crystal structure for that because nobody thought to measure it, or maybe people tried, but it never worked. There could be undetected interfaces that were predicted correctly, but we can't say that they're correct because we don't know. Okay, so I think that's the end of the story. There's more detail there if you want to detail the feature importance. So we can predict protein interactions from sequence. We use the evolutionary neighborhood by using SciBlast. We have a web server. Its performance is quite stable. Also, the difference between the training set and the sets is reassuringly small. That's why we use random forest, because they're quite stable in that respect. We're better than other sequence-only predictors. And of course, if you have a structure, use it. But if you don't, then we're your next assessment. Okay, that's the story. And of course, I should thank Xingzhen, who was a PhD student who did it. Paul, who was a master student who did a lot of his work. Wim Franken is a collaborator in Brussels who created Dynamine. And you know, yeah, he's responsible for paying my job, which is very, very nice. Okay, and this I should have updated this. I actually gave this lecture on a workshop last year. Okay. Are there any questions? Further questions? We have a few more minutes for some questions.
Have you tried using another classifier than random forest?
No. Not yet. Well, we tried. We're not machine learning experts. And then random forests, everybody tells me random forests are quite insensitive to our training, so that seems like the same place to start. We're right now trying to do, we're redoing this work with neural nets and trying to go to deeper nets, so you can actually, you don't have to use the other predictors first, but you can just have the proper, what's the word for it again, auto something. Autoencoder. You can actually train an autoencoder, so it gets the features that you need straight away. But that's quite a lot of work, so that's being done.
For going to neural networks, have to try to run a search grid or any kind of parameter optimization?
We've done some of that, but the first thing is to search for appropriate neural net structures, and then see which ones work well or not, and then go to make a parameter switch.
No, but within your model, not
within the within the.
Yeah.
I don't know. I don't know if we already did that. Other questions?
Do you have any idea why, if it was trained with both data sets, why it could work for the homo gamma, but why it would perform worse for the hetero?
That's a good question.
You would expect it to be both.
You mean why the combined works worse in this case?
Yeah.
Actually, that's sort of what you expect, right? You're trying to aim for two targets, and then you typically get a bit worse in both. If you want to be more generic, you're probably less good than a specialized predictor for one of the two. So for me, the surprising thing is actually that this one is not worse. The combining is not worse for the homomeric prediction. But the homomeric test set is actually, training set, sorry, is actually, this is the number of proteins in the set. It's actually bigger then this is the heteromeric training set. So it's about 1 to 4, 1 to 5. So if you combine them, you just concatenated both sets. So this set is actually dominated by the homomeric interactions, but it still performs quite okay on the heteromeric set. Quite a bit better than the one that's only trained on homomeric interactions. So part of the answer is because the training set is just dominated by the homomeric proteins, because we have more of them. We're also now collecting more training sets or more data to get a new. We've used up our validation set, so we need a new validation set. And we also need a bigger training set. Certainly we want to go to deep nets, just then we need all the. Other questions? One last question, I think. Otherwise, I run into all the time. No? 5-minute coffee break? Yeah. Can you guys be back at 10 to 10?
Or do you need